Welcome to an exciting journey into the science behind cooking, where physics, chemistry, and thermodynamics come together to create delicious food. Cooking is not just an art. It is a precise science involving heat transfer, molecular transformations, and mechanical processes that turn raw ingredients into extraordinary dishes. Let's start by understanding what food science actually encompasses. Food science is the study of the physical, chemical, and biological properties of food, combining physics, chemistry, biology, and engineering. All these disciplines converge in the kitchen, where physics governs heat transfer, chemistry controls molecular reactions, biology affects fermentation, and engineering principles guide cooking techniques. Let's explore how thermodynamics, the science of heat and energy, is fundamental to cooking. When we cook, heat transfers from the heat source to food through three primary mechanisms: conduction, convection, and radiation. Conduction is direct heat transfer through contact, like when a steak sears on a hot pan. Heat flows from the hot pan directly into the meat. The Fourier law describes conduction, where Q is heat flow, K is thermal conductivity, A is area, and dt over dx is the temperature gradient. The thermal conductivity K tells us how efficiently a material conducts heat. Metals have high K values, which is why copper pans heat quickly. Copper has a thermal conductivity of about 400 watts per meter Kelvin, making it excellent for even heat distribution in cookware. Convection involves heat transfer through fluid motion. Hot air or liquid moves, carrying heat with it, like when boiling water circulates heat throughout a pot. Newton's law of cooling describes convection, where Q is heat transfer, H is the convection coefficient, A is surface area, and delta T is temperature difference. Here's an interesting question. Why does water boil at exactly 100 degrees Celsius at sea level? Water boils when its vapor pressure equals atmospheric pressure. At sea level, this occurs at 100 degrees Celsius, or 373 Kelvin. At boiling point, vapor pressure equals atmospheric pressure, which is 325 pascals at sea level. Radiation is heat transfer through electromagnetic waves requiring no medium. When you grill food, infrared radiation from hot coals directly heats the food. The Stefan-Boltzmann law governs radiation, where Q is radiated power, epsilon is emissivity, sigma is the Stefan-Boltzmann constant, A is area, and T is absolute temperature to the fourth power. Let's calculate. A surface at 500 Kelvin radiates about 3,500 watts per square meter, which explains why grills and broilers cook so effectively. Now let's explore the fascinating chemistry that transforms ingredients during cooking. The Maillard reaction is one of the most important chemical reactions in cooking, creating hundreds of flavor compounds and brown colors in cooked food. The Maillard reaction occurs between amino acids from proteins and reducing sugars, requiring heat above 140 degrees Celsius to proceed rapidly. When amino acids meet reducing sugars under heat, they undergo complex reactions producing melanoidins, which give bread crust, roasted coffee, and seared meat their characteristic colors and flavors. The Maillard reaction proceeds optimally between 140 and 165 degrees Celsius. Below this, reactions are too slow. Above this, burning begins. Caramelization is another crucial reaction where sugars break down under heat, creating new flavor compounds in characteristic brown color. When sucrose, C12H22O11, is heated above 160 degrees Celsius, it undergoes thermal decomposition, creating hundreds of new compounds, including caramel color and flavor. Here's an important question. Why does caramelization require higher temperatures than the Maillard reaction? Caramelization requires breaking carbon-carbon bonds in sugar molecules, which needs more energy than the Maillard reaction, typically starting above 160 degrees Celsius. Understanding protein denaturation is crucial for cooking meat, eggs, and many other foods. Proteins are complex folded molecules. When heated, they unfold or denature, changing texture and properties dramatically. Native proteins are tightly folded. Heat provides energy to break hydrogen bonds, causing proteins to unfold into denatured, extended forms. The Gibbs free energy equation governs this process, where delta G is free energy change, delta H is enthalpy, T is temperature, and delta S is entropy change. Egg white proteins denature around 63 degrees Celsius, changing from transparent liquid to opaque white solid as proteins aggregate. Different proteins have different denaturation temperatures. Fish proteins denature at 40 degrees, while beef collagen requires 65 to 70 degrees. This graph shows how protein denaturation increases exponentially with temperature, which is why precise temperature control is crucial in cooking. Phase transitions, where substances change between solid, liquid, and gas states, are fundamental to many cooking techniques. Water can exist as ice, liquid water, or steam, and cooking uses all these phases strategically. The latent heat of fusion for ice is 334 kilojoules per kilogram, meaning this much energy is needed to melt 1 kilogram of ice at 0 degrees. The latent heat of vaporization is 260 kilojoules per kilogram, significantly higher than fusion, explaining why boiling requires much more energy than melting. Let's answer an everyday question. Why does it take so long to boil potatoes? Water has a high specific heat capacity of 4.18 kilojoules per kilogram Kelvin, meaning it takes a lot of energy to heat water, plus the latent heat for phase change. Water transitions from ice to liquid at 0 degrees Celsius, then to steam at 100 degrees Celsius under standard pressure, with each transition requiring substantial energy input. Many foods are complex colloidal systems where small particles are dispersed in another substance. Emulsions are colloidal systems where oil droplets are dispersed in water or water droplets in oil, stabilized by emulsifiers. In mayonnaise, oil droplets are dispersed in water, stabilized by lecithin from egg yolk. The emulsifier molecules have one end that likes oil and one that likes water. Surface tension, force per unit length, determines droplet stability. Emulsifiers reduce interfacial tension, allowing stable emulsions. Mayonnaise is a remarkable emulsion containing 70 to 80% oil, yet appears as a thick cream due to billions of microscopic oil droplets. Osmosis and diffusion are crucial processes that affect brining, marinating, and preservation. Osmosis occurs when water moves across cell membranes from low to high solute concentration, driven by osmotic pressure. The Van Hoff equation relates osmotic pressure Pi to concentration C, the gas constant R, and temperature T. When meat is placed in brine, water moves into the cells by osmosis, making the meat juicier. Salt also diffuses in, adding flavor throughout. Fick's first law describes how substances diffuse from high to low concentration at a rate proportional to the concentration gradient. Fick's law states that flux J equals negative diffusion coefficient D times the concentration gradient dC over dx. In meat, salt diffuses at approximately 1 millimeter per hour at room temperature, which is why large roasts need long brining times. The mechanical properties of food determine its texture, one of the most important quality attributes. When we bite food, we apply stress, which is force per unit area, and the food deforms, creating strain. Stress sigma equals force F divided by area A, measured in pascals or newtons per square meter. Strain epsilon equals change in length delta L divided by original length L0, a dimensionless ratio. Stress-strain curves reveal material properties. Brittle foods like crackers show high stress at low strain, while ductile foods like bread dough deform extensively. Young's modulus is the ratio of stress to strain in the elastic region, measuring how stiff a material is. Young's modulus E equals stress divided by strain. Fresh bread has E around 50 kilopascals, while stale bread reaches 200 kilopascals. Enzymes are biological catalysts that speed up reactions in food, both during preparation and storage. Most enzyme reactions follow Michaelis-Menten kinetics, where reaction rate depends on substrate concentration and enzyme properties. The Michaelis-Menten equation shows reaction velocity V equals Vmax times substrate concentration divided by Km plus substrate concentration. This curve shows how reaction velocity increases with substrate concentration, approaching a maximum velocity Vmax when all enzyme active sites are saturated. Polyphenol oxidase is an enzyme that causes cut apples and potatoes to brown by oxidizing phenolic compounds when exposed to oxygen. How can we prevent this browning in cut fruits and vegetables? We can prevent browning by lowering pH with lemon juice, reducing temperature through refrigeration, or removing oxygen by vacuum sealing. Let's work through practical heat transfer calculations for real cooking scenarios. Suppose we need to heat 2 liters of water from 20 to 100 degrees Celsius. How much energy is required? The heat equation is Q equals mass times specific heat capacity times temperature change. We have 2 kilograms of water with specific heat capacity 4.18 kilojoules per kilogram Kelvin. The temperature change is 80 Kelvin or 80 degrees Celsius. Therefore, Q equals 2 times 4.18 times 80, which equals 668.8 kilojoules of energy needed. Using a 2 kilowatt stove, which is 2 kilojoules per second, this heating takes approximately 5.5 minutes, assuming perfect efficiency. Understanding thermal diffusivity helps us predict cooking times for large pieces of meat. Thermal diffusivity alpha determines how quickly heat diffuses through a material, crucial for cooking timing. Alpha equals thermal conductivity K divided by density ρ times specific heat capacity Cp. For beef, thermal diffusivity is approximately 1.4 times 10 to the minus 7 square meters per second. Heat penetrates meat slowly in concentric layers. The center of a large roast takes much longer to reach temperature than the surface. For a 5 centimeter thick steak, let's estimate the time for heat to penetrate to the center. A rough estimate for thermal penetration time is T approximately equals L squared divided by 4 alpha, where L is thickness. Substituting our values, we get approximately 100 seconds or 18 minutes for significant heat penetration, explaining why thick steaks need patience. pH profoundly affects food chemistry, texture, color, and safety. pH measures hydrogen ion concentration on a logarithmic scale from 0 to 14, where 7 is neutral. pH equals negative log base 10 of hydrogen ion concentration in moles per liter. pH affects enzyme activity, vitamin stability, and even food safety, making it essential to understand pH in cooking and food preparation.